I'm Leo Reyzin, and I'm going to talk to you about my work on proofs of space with maximal hardness. So what is a proof of space? A proof of space is a protocol that allows a prover to fill up some space and then periodically convince the verifier that the space is still filled up and still being used. So the prover and the verifier will perform an expensive initialization once, where the verifier gives a small input x to p, and using a function f, the prover expands this small input to a very large output. That's the filled up space. The large output is the filled up space. And then in most schemes, the prover will also convince the verifier that this output y was computed correctly or almost correctly, and will provide the verifier with a short commitment like a Merkle root to this y. And then periodically, where t denotes the period, they will perform an execution protocol in which the prover will convince the verifier that the prover is still storing this y. So the verifier will query the prover, and using some lookups in y, the prover will return an answer. And these lookups are going to be small, constant number or logarithmic number of lookups. So the prover is not going to read all of y. And the security we want to ensure is that the prover, even if malicious, will commit to at least 1 minus space gap times the size of y of storage. So almost all of y, maybe just space gap less. So the security goal is that if you're going to be answering while storing less than that, then it's going to cost you more in computation than just maintaining the storage for the time period between queries. So if we think about the cost on one axis and the time on the other, and the cost of storage is roughly linear in the amount of time required, we can put on the y-axis the computational cost of answering if you're not storing enough, and then this vertical x-intercept is the point where the cost of computation is equal to the cost of storage. So polling needs to be to the left of this line. The polling period needs to be short enough so that erasing and recomputing doesn't pay. It's cheaper to just store than to compute. And because polling is a protocol people must run periodically, we'd like this time period t to be as short as possible. And that means we would like the computational cost of answering to be as high as possible if you're not storing enough. We also want this space gap, this amount that you can reduce your storage by for free without adding any computational costs. We'd like that to be small. Otherwise, malicious provers may be able to get away with storing a lot less than honest provers and not incurring any computational costs. And in a proof of storage system, for example, malicious provers can subvert the system by taking over just a small fraction of storage because if the space gap is big, then maybe they need to store a lot less than honest provers who are going to store all of y. And that would be a problem in a proof of storage system. So now let's do a different graph. Let's, on the y-axis, put the cost of answering, but on the x-axis, let's put the amount of storage. The cost of answering, computational cost of answering, even if you're storing nothing, will never exceed the cost of computing f, because you can always recompute f from x. X is very short, so the cost to p star will not exceed that value. And the storage by p star will never exceed y. And basically, we can plot a graph which is the cost of answering when storing some amount. If you store everything, your cost of answering is essentially 0. If you're storing nothing, your cost of answering is essentially the cost of f. And we would like to understand this trade-off. So a type of theorem we would like to prove is that if your storage is at most 1 minus space gap times the size of y, then your cost is at least 1 minus cost gap times the cost of f. So our goal is to prove this for a small cost gap and space gap. So now let's talk about what's known in existing work. Most constructions actually have cost gap and space gap very near 1, while we want them to approach 0. And in fact, only 2 constructions have them approaching 0. Ben Fish has a construction where space gap approaches 0, but cost gap approaches 1. So it looks like this in the picture. Its practical deployment in Filecoin has space gap of 0.2. So we know that a cheating prover has to store at least 80%, which is good. But the cost if you don't store 80% is only 1/55th of the cost of initialization, which is not great because that leads to a small time t between executions. A construction by Pietrzak has both space gap and cost gap approaching zero, but unfortunately the cost of initialization grows very fast as cost gap and space gap get smaller, making the construction impractical already for space gap of a half and cost gap of 3/4. So the picture looks like this. So our result is to get space gap and cost gap to approach zero, while the cost of initialization grows reasonably with the cost gap and space gap. And moreover, we get practical constants, not just practical theoretical growth with our result. So the picture looks like this. The cost gap and the space gap are small, so the cost of answering is close to the cost of f if you're not storing almost everything. Now, a couple of disclaimers. Most works, including our work, are lower bounding total cost, the total amount of computation you need to do. But in contrast, both Fish and Pietrzak are able to prove that a malicious prover who doesn't store enough must work sequentially, which means that instead of measuring simply the cost of computation, we can measure the time of computation, and the verifier can simply time out, making sure that even an irrational prover who does not consider its own cost cannot win. This kind of security is called security in the latency model. And the second disclaimer is that all works, including ours, restrict the adversary to an idealized model of computation. First of all, we're going to assume that the adversary works in the random oracle model. The only way you can access the oracle is to query it. And second, we're going to assume that the random oracle outputs are atomic. They're either fully stored or fully gone. And unfortunately, this assumption seems to be needed in the cost model. We don't know how to get rid of it, but in the latency model, it is possible to get rid of it. Okay, so now what I want to do is present our construction, and it's more or less the construction from Ben Fish's paper. And what's different about our construction is the analysis. So step one of our construction is to take the input x and push it through this graph. What do I mean by pushing it through the graph? I mean that there's a public graph fixed once and for all. Everybody knows it. It has n nodes, and each node is going to be labeled, where the label is the hash of the labels on the incoming edges, starting with hash of x. And the hash is modeled as a random oracle. So the desired property of the graph here is the following. Suppose I have a subset of nodes of some constant weight pi. So in this example, the nodes are grayed out, and the subset that I have left is a fraction of the original graph. It's 80% of the original graph. That's my pi. Then in that subset, there will be a single sinc subgraph of weight at least alpha pi. Why do I want a single sinc subgraph? The sinc of the subgraph depends on a lot of other elements in the subgraph. It depends on alpha pi nodes. So in order to compute the sinc, you have to compute a lot. That is a useful property. We'll see why it's useful later. This property is called predecessor robustness. It's similar to a more commonly used property called depth robustness, and it's just a generalization. Depth robustness is a special case. Unfortunately, it appears difficult to prove for good parameters. We know it is possible to get it for constant pi and alpha pi using logarithmic degree, but it's reasonably to conjecture it for specific parameters. And for example, if the number of nodes is roughly a billion, and we use cleverly chosen random edges within degree 6, then we can reasonably conjecture that if pi is 0.8, in other words, the subset of nodes is 80% of the graph, then there will be a single sinc subgraph in that subset of weight 20% of the graph. Now, our proof does not depend on this specific conjecture. Any constant pi and alpha pi will do, and you can get those with logarithmic degree. Now let's talk about step 2. In step 2, we will take copies of this graph, put one under the other, and connect them using an expander. What are the properties of this expander graph, of the vertical graph that we want? That any set of nodes at the bottom needs to have a lot of ancestors at the top. So the red are the bottom nodes, the blue are the nodes that are connected to them, and we see them more blues than red nodes. And here's the graph of the expansion that I want. And basically what I want is that small sets grow exponentially, and big sets, what's left between the set and the rest of the graph shrinks exponentially. And it's not too hard to get a random graph with a constant in and out degree, let's say 8, will give me what I want with high probability. And then step 3 is to keep doing this in many layers. So we're going to have L layers. Think of the width of the graph N as very big. The layers is not terribly big, so the width maybe is a billion, and the height is in the tens. And so we have all these layers of the graph, and that is our final graph. So the prover will compute all of this on input X. And then we'll Merkle hash all the nodes and prove correctness. How will you prove correctness? The verifier will choose a random node. The prover will reveal the neighbors of that node. And the verifier will check that all of them were revealed correctly according to the commitment to this graph, and that the hashes of the neighbors are equal to the chosen node. And that way you will be able to prove that locally the graph was computed correctly. And actually you can do this for entire columns at a time because the graph is symmetric. Um, and basically, the prover can cheat in at most a constant fraction delta of each layer. And for this talk, for simplicity, we assume that this delta is basically 0, that the prover really did everything correctly, or delta is so small that we're not going to worry about it. And now we're done. And what is the output y? The output y is not the entire graph, it's just the bottom layer of the graph. And now this construction is a small modification of the stacked depth robust construction from Fish. We call it stacked predecessor robust. Here its main antecedents. And what we need to prove is that if some parts of y are erased by the malicious prover, it'll take a lot of work to recompute them. So let's simplify the graph for a second. And what is our proof goal? The proof goal is to prove that every bottom layer node depends on many nodes above. So let's take a bottom layer nodes. Let's say these blue nodes are the ones it depends on in that particular layer. The expansion will say that above it, it depends on even more nodes. And more expansion will say that above it, it depends on even more nodes, maybe now the entire layer, in fact. But of course, the adversarial prover can store some values because the adversarial prover has storage. So if the adversarial prover stores this particular value that I darkened on the screen or cheats on this value and therefore doesn't even need to know it, then there's no need to recompute its predecessors. So these predecessors disappear and those predecessors disappear, and now you have much less computation simply because you stored one piece of the graph. And we will call storing a piece of this graph uh, putting a pebble on the graph. So a malicious prover is going to put a pebble on the graph, and that's what corresponds to knowing a label. And the adversary has a total of 1 minus space gap times n pebbles, because y is of size n, and the adversary is trying to store less than 1 minus space gap times n. And a footprint of this red node that I picked at the bottom of the graph um, is the set of ancestors that are reachable with an unpebbled path. In other words, you can get from this red node to an ancestor without touching any pebbled path, then this ancestor is in the footprint of the red node. And of course, a large footprint corresponds to lots of computation. The malicious prover would have to recompute every node in the footprint. And the result of Ben Fish is that a certain fraction, space gap over 2, of the bottom layer nodes have a footprint that is at least alpha pi times n. Remember, alpha pi is the predecessor robustness parameter, n is the layer length. So you get a footprint that is a fraction of one layer. That's certainly not a big footprint compared to the size of the graph, but it is something. That's where the cost gap that is fairly large comes in Ben Fish's result. Notice that you can't do much better than space gap over 2 for the number of bottom layer nodes that have any footprint, because the prover could be remembering 1 minus space gap of bottom layer nodes anyway. So space gap is the most you can do. We get space gap over 2. Our result differs from Ben Fish's result in that we prove that this many bottom layer nodes have a footprint that is almost the entire graph. Remember, L is the number of layers and n is the width, so the total graph size is Ln, and we're able to prove that it is the footprint is almost Ln. Thus, if the verifier queries a certain number of random positions to over space gap, then the expected cost to the verifier will be approximately the cost of computing f, which is exactly what we want. One can view this result as a result on predecessor robustness. In some sense, we're amplifying predecessor robustness by showing that the unpebbled subset of the graph, that's the subset that we chose, has many single sync subgraphs, and those subgraphs have most of the nodes, and they end at the bottom. Now, why is this proof challenging? If we look at the graph again, if we look at the horizontal edges, remember the property of the horizontal graph. It says that in any sufficiently large subset of a single layer, there's a large single sync subgraph. But how do you even get to a large subset of a horizontal layer? On any given horizontal layer, the adversary can place enough pebbles for you to not have a large enough fraction. So we can't, for any given layer, say that there will be a large subset there. And then for vertical edges, we have a different challenge. Expansion arguments work for sets of nodes. But we start with just one node. And just one node will have only a few ancestors. And if it has a few ancestors, you can place pebbles and remove those ancestors, and that will completely eliminate its footprint. So with any one node, you can always pebble it away. So any one layer can be pebbled away, any one node can be pebbled away. How do we do the proof? So here's our graph. The first step is to prove that many bottom layer nodes have a reasonable size footprint in most layers, and we'll call such layers fertile. To do this, we won't actually start with a single node, rather we will start with a large set of nodes, denoted here in purple S, and we will look at its footprint, and we will prove that it has a footprint of at least pi in most layers. Recall predecessor robustness. It says that in any subset of nodes of weight pi, there is a single sync subgraph of weight at least alpha pi. So let's look at such a subgraph. Let's say in layer 4, it has weight pi. So there's a sink in purple on layer 4. There are the nodes that are feeding into that sink. And the sink is in the footprint of S. And by definition of footprint, that means some node in S has a link to that sink. And that means this node has the whole subgraph of size alpha pi in its individual footprint, which is exactly what we wanted to prove. So step 1 says there are many red nodes that are connected to many green layers, and each green layer has a footprint of at least size alpha pi. The next step is to prove that there is some layer M that is just a little bit above L, so not too high, with the following property. There is some fertile layer below it whose footprint exceeds the number of pebbles above M. The main idea here is to argue the following. For each fertile layer, either the footprint will grow, or pebbles are being spent to stop it from growing. And eventually, as you go up, the footprint will exceed the number of pebbles that are remaining. So in this example, the fertile layer 9 started growing, but then a lot of pebbles were spent at layer 6 to stop it from growing. But then fertile layer 4 keeps growing, and eventually its footprint will exceed the number of pebbles that are remaining. So here's our layer M that is above some fertile layer to which a red node is connected. And its footprint is big enough to overcome the influence of pebbles above it. So step 3 is to prove that this footprint will expand above M to almost the entire graph above. Let me conclude. So we do achieve cost cap and space cap going to 0, which means if you try to save even a little bit of storage, your costs go up, and we do so with practical constants, which are in the paper. But I want to talk about a couple of open problems. First, to get good constants, you need good predecessor robust graphs, which we know how to build theoretically, but with good constants currently requires a conjecture. Second, can we do what we do in this paper, but also guarantee that the computation of P star has to be sequential, because that would mean security can be enforced by the verifier via a timeout, rather than simply by arguing that the costs to a malicious prover are too high. Thank you for your attention. The full version of the paper is on ePrint at 2023-1530.